All right, now that we've gone ahead and we kind of have talked about how to add a library and add our first part, we're going to go ahead and go through actually putting down the schematic for this design. We'll do a lot of this in fast forward or skipping forward, but we'll definitely stop when there's something of interest. But basically the process is going to be taking the schematic which we showed earlier, this very rough schematic from a piece of graph paper, and converting it into the schematic here within the software itself. So it's just a matter of adding pieces one at a time. So we'll be back in touch after we've got a bunch of things added. Okay, so now that we're kind of laid out a few parts, I want to kind of touch on a couple things. You'll probably run into this if you watch any of the online tutorials as well about KiCad. But one of the most important things when working with PCBs is to have a grid, and choose a good grid for use in the design. It's not as important within the schematic, but you can definitely make a schematic look cleaner if you start everything on one grid and you maintain the same grid. So just to kind of clarify for this, we do have a grid going on here in the background, and I'm just going to make sure that it's a grid that kind of makes sense for me, because I want to be sure that when laying out my parts, I am able to have everything line up and kind of look nice, for lack of anything else. So to do that, I am going to adjust my grid settings. If I can remember where that setting is. Here we go, under the schematic editor options. So setting our default units and our grid size in mils. Now mils don't really mean as much in a schematic again. However, if this was to be printed out, this is where this would come into play. But making sure that it's a nice round number that can be divisible. In this case, it's 50, which is divisible by 10, divisible by 5, and divisible by 2. So I can adjust that as needed if I really need to just tweak something just to make it look right. So we're good to go on that. From there, since I actually had the original grid, everything's already set in place. Otherwise, I would go ahead and I would bump everything to make sure it's lined up properly. So we'll go ahead and we'll wire up this first little bit just to make sure that we've seen an example of how this wiring can go. It's also pretty important to do this because the endpoints of where the parts are made, as long as they're on the same 50 mil grid as everything else, actually allows for us to quickly connect rather than having to zoom in great detail to actually make those connections. All right, I'll go ahead and keep getting it wired. So here's an example of something that's kind of a little obnoxious, where if you notice that as we zoomed in here, I moved this capacitor just a few moments ago, and during that move it actually became disconnected and it no longer appears to be there. So to correct this, we need to go ahead and activate the place junction tool. Just drop a junction there so we know that it's in place. Okay, back to laying it out. One useful thing to remember is that KiCad has a set of keyboard shortcuts which allow you to do things a lot faster than using the graphical menu. To approach these or to find them, the easiest thing to do is just to hit your question mark key, and then this will pop up a hotkeys list. This list is accurate as of what you're currently doing and has a lot of options here. One of the things that's really kind of important for me is like this ability to move schematic item. So this is really challenging. Normally when you're messing with a part, you tend to move the whole part because that's what the default interface using your mouse does. But in actuality, if I wanted to, for example, fix where this battery is so that I could read it, I can just highlight just the battery, press M, and then lo and behold, once I've picked it, it'll actually let me move just the thing I want to have moved rather than the whole component. So that's pretty useful also if I want to do things like rotate. So for example here, if I want to rotate just that text, not the whole part, I'm highlighting over the text before I click something, which is the R key in this case to cause a rotate, and then the M to do a move. So that's dang useful to be able to actually adjust the thing that's directly underneath of your cursor at the time, allowing us to get a much cleaner design. Okay, so this is our basic power supply portion of the board. Next thing I'm going to do is I'm going to go ahead and I'm going to lay out the Mega 48 part. That's also a piece of our design. And then I'll be back in touch once we're done entering the entire schematic. Okay, so I've put down the Mega 48 now, but one of the things that's important with a microcontroller specifically is to be able to label the nets and have them be virtually connected within the schematic. If we don't do something like this, we end up with a lot of wires running in seemingly random directions to get everything connected. So we can clean up the schematic a lot by doing this. Some people will suggest that instead you actually do everything in this fashion, where your connectors all have net names associated with them and your parts have net names associated with them, but there's no actual connections for any of them. I, on the other hand, like to, whenever reasonable, to actually do the wired connection between things, because to the eye, the graphical flow and the flow of the circuit is much more obvious. But to add these net names, we've selected this place net name tool over here, and then we're just going to go ahead and we're going to label this. This particular pins are going to be used a lot, net's going to be used a lot as MOSI. So we're going to make sure that we have the MOSI enabled. Then we're going to drop it into place. Then we're going to go ahead and we're going to label this one, and this one is a MISO. And you notice I could change the size of the text if I wanted to, but this seems to be fitting just fine. So we'll leave it alone. We have an S clock. It's going to be an important one. And then this one we're going to use is going to be important because we're going to use the reset. Now this particular reset, you'll notice, is an active low. That's what the bar over the word reset means on the chip itself. If you can't add a bar to a net name, a common one is to put a subscript lowercase n on the end of it, or in some cases an underscore in the beginning. We're going to go ahead and we're going to go with the reset, and then we're going to do an underscore n, assuming KiCad will let us do this, which it does. And then we'll put it right here so that we know that that is an active low reset signal. Okay, now as you've seen this, I'm going to go ahead and I'm going to add in the connectors that are needed for this board, and then I'm going to hopefully wrap it up before I talk to you again. So one of the things that's important when you're laying out a digital circuit is to make sure that your various digital ICs have local capacitors very close to their power and ground pins. And these pins act as a kind of a little bit of local energy, so that if there's noise in the power supply line, or if the chip itself needs a little bit of extra energy right then, there's a reservoir waiting near those. Sometimes these are called crap caps because they remove the crappy voltage levels from the voltage line itself. They don't remove it, they supply energy to counteract it, would be a more accurate term. And those are going to be placed very close to the pins of the chip during layout. However, in the schematic portion, where their layout isn't really important, they can be placed anywhere. There's a lot of methodologies you could choose to implement. In my case, I usually like to put kind of my odd power stuff in one location. So you can see that I'm starting to build that here, where I'm going to make some extra power and ground connections for the outside world. And then I'm going to actually have my two crap capacitors available for the two pins of my Mega 48 also in this same area. So I'll go ahead and again finish this up. So what I'm laying out right now is going to be the programming header. Most Atmel series chips now owned by the Microchip company have this AVR ISP 6-pin interface that you can enable, and then there's a myriad of programmers out there that will actually put code on the microcontroller. This pattern of 6 is exactly as stated in this diagram. But we need to go ahead and implement it so that we're able to program our chip. To do that, I'm just going to connect it to the proper pins. And again, remember that as long as I'm doing a net name, this system will connect these things for me. Okay, I think that's just about got it. The last thing I want to do is I want to go ahead and I want to edit this portion to make sure that I've locked what this thing is. So that's under File, Page Settings. And then here I can actually add the information and I can carry it across multiple sheets. So this is going to be my version .1. This is going to be the ECE340X demo board. And we'll say Oregon State made this. Why not? That sounds like a good thing. And we can also add other comments and things along the way. And we could even change the size of the paper. In our case, we probably would want to use US letter 8.5 by 11. This might put some things off of my page, so we'll go ahead and we'll check that. But it looks like I lucked out here. Yeah, and it's definitely ready to go. One of the things that I could also add here would be today's date, as well as to add my own name so that people would know who to come complain at, assuming the system didn't actually work. All right, so that's the basics of creating a schematic. I'll let you go ahead and look at this. I'll also upload this file available for you guys to get your hands on. In our next set of videos, we'll go ahead and go through the process of converting this to a net list and making a PCB. Along the way, we're going to find that we're going to need to make a part or two, at least a geometry or a decal for the PCB to match some of these parts that we have, and then we might even come back to this and edit it. At this point, this particular schematic is not known to work. That's just part of how it is sometimes. I did not take the time to verify a couple things that I noticed along the way. I will point some of those out though since we're talking. One of them, a VCC traditionally has an inductor and a capacitor here to isolate it from the digital VCC. I don't think it's going to be a problem. What it essentially does is it makes sure that any analog digital measurements done by this processor are very clean by isolating the two power lines. I still think it'll work, but it might be something I go back and fix after I do a little more research. The other thing is this particular connector that we're using here. We're going to have two different styles. One's going to be a JST connector, a 2 millimeter pitch JST connector, and the other one is going to be the actual battery terminals that are specified in the original PDF scan that went out about this project. I'm not sure, but I might be wanting to change this component into two individual test points, each of those test points being one of those connectors, and then when I lay out the PCB, actually setting them to the proper dimensions there. Those are the things that I know of right now I'm kind of curious about, and they might change even before we see the next video. All right, everyone, thanks for watching.